So the Doppler effect is a relative change in frequency or the wavelength due to the motion of the source and observer. And different applications like Doppler radars are there, speedometers, redshift, and same thing. We have the ultrasonic test units that also uses the same concept of that is a pulse echo technique. What is a pulse echo technique? In a pulse echo technique, it's like we are sending the pulse. In a pulse echo technique or a pulse echo method, what we use, we send a pulse. Pulse means a small signal is there, which we call like one wave or less than one wave. We call that as a pulse. So what we do, we send a pulse. When we send the pulse is sent. Like example, say the first one, when we place a detector, here a transducer is there. So when we send the pulse is sent, it will strike and it bounce back. So if we want using this pulse echo technique, we can identify, we can find the width of an object, the distance from which the pulse is reflected. So the speed of the wave is known, like if we are using sound waves, any electromagnetic wave, speed in the medium is known. So speed, which is here is v, the distance which is travel, example, if I say width of this object is d. So what is the distance traveled by this pulse? Because it is being sent from the source and then it receives. So the distance traveled by this pulse is 2d. Why 2d? Because it's going and coming back. And the total time to send and receive the pulse is t. So if you use a formula like v is equals to 2d divided by t. So if we need the distance, the width which the pulse is being bounced back, so it will be v into t divided by 2. And remember, this t is not the time for the pulse to send, it's the total time taken by the pulse, like how much time it take to return back. So that time, like example here, when the pulse is sent, that is we receive a peak here. When it goes inside and then bounce back and we receive it again from the bottom, we receive, that is another pulse, like the signal is detected. And the distance between the two, like the time interval, because it's a CRO, cathode ray oscilloscope. In CRO, we have the x-axis is a time base. When we say it's a time base, it's like each box is having a certain unit. It can be in millisecond or microsecond. So how many boxes, what we will do, we will count like how many boxes are there or how many uh, frames are there between the two pulses. So if I say the distance between the time interval between the two marks is say 20 milliseconds. So how much time it took to receive or return back? Yeah, t is the total time it goes and come back. So say one, two, three, four, five, six, and seven boxes are there. So if seven boxes are there, what is the total time? So it will be 7 into 20 milliseconds, which is equals to 140 millisecond. So it means 140 millisecond it took to go down and come back. So that is the total time. V is the speed of the wave which we are using. Like if we are using, it's an ultrasonic, so we are using a sound wave. We know the speed of a sound in different materials, so V is constant. So V multiplied by T divided by 2, what we get? We get the distance or the width. So using this, we can also identify the cracks in the metal, because like if there is no crack, then the difference between the two peaks will be longer. But if there are cracks in the metal, then some part of the wave is reflected from the crack. So as a result, we'll get multiple peaks, multiple reflection. So using this technique, the ultrasonic test, we can identify if there are cracks or no. This is also called a pulse echo technique. A pulse echo technique means we send a small signal and it bounces back from the surface. When it enters the material, it bounces back from the different surfaces, different density of the mediums. As a result, we can identify the thickness of the material. It's also used in sonar, sound navigation, and ranging. It is also used there. So the simple concept is that we have a source. When we produce a wave on a CRO, we get one peak. That this is a point where we receive the signal. Then this wave travel, strike, and bounce back. If the width of this object is d, and the wave does not accelerate in the medium, so speed is distance divided by time. So speed at which the wave travel is v. What is the distance travel? Because the wave travel down and come back, so the total distance travel will be 2d. And when we receive this back again, we receive another pulse, but it will be a lower intensity because some of the wave is being, some of energy being absorbed. So the height of the peak, the intensity of the peak will be lower. And t is the total time interval between the two peaks. How much time interval is there between the two peaks? That is t. And how we calculate this t on a CRO? CRO is known as a cathode ray oscilloscope, which is a device which can be used to observe the wave motion or finding the time period or the frequency of the waves. So it is the CRO is having the markings grid. It has grid, like labels are there, markings are there, and it is having the x-axis is called a time base. The x-axis is a time base. Using the x-axis, we can find the time. So when we send the first pulse, when it is produced, this is a peak we receive on the CRO. When the wave travel and it bounce back, this is a new peak we receive. So how much time interval is there between the two peaks? How we can work out using a setting of the time base of CRO, we can work out that. Like each box, each grid, like spacing between the two lines, say, let's take an example, say it is 2 millisecond. So from how many milliseconds are there? One, two, like how many lines are there, interval? So 1, 2, 3, 4, 5, 6, and 7. So 7 markers between the two peaks. So it means it will be 20 multiplied by 7. It means the time interval between the two pulses is equals to 140 milliseconds. So using this time and using the speed, we can know the width of an object or the distance of this, like how much distance the wave cover from the reflecting surface, or distance between the source and the reflecting surface. Is it clear? This one, the pulse echo technique? Any doubt in this? So let's take like example, the first one, when we produce a wave, this is a peak we receive. Then the wave bounce back, we receive another pulse. That is, if there was, this is a time, but when there is a crack, some part of the pulse will be reflected. So that is reflected from the crack. Then if there's another crack, some part will be reflected from the second crack. So using this, we can also identify the position at which the crack is located. Like example, if I want to locate what is the position of the first crack. So this distance is x and the speed of the wave is v. So what is the distance travel? So speed is distance divided by time. Speed is v and the distance travel will be 2x. Why 2x? Because the wave is going towards the crack and then it bounce back. And t is a time interval. So how I will know the time interval? I will just use the time scale of the CRO, cathode ray oscilloscope, and find what is how many units are there, how many intervals between the two peaks, and that will give us a time. So we'll get the time, we know the speed, so we can work out the distance or the spacing between like the distance of the crack from the top of this surface. Some questions related to Doppler effect and the pulse echo. You can use the chat to answer. as it's a MCQ. S is a source of a sound of frequency Fs, and S is accelerating towards an observer 1. Like it's moving towards and it is also accelerating. Two things are happening. It's moving plus it is accelerating, like the speed is increasing. F naught of the sound heard by O will be like F naught is a frequency of the sound which is received by the observer. Fs is a frequency of a sound produced by the source. What could be the right option? You can use a chat to answer this. First, two options are totally wrong. Smaller. It cannot be smaller, it should be higher. And then, because it is if it was moving at a constant speed, it will be greater and continuously increasing. Why? Because if the object is moving at a higher speed, there will be a greater change in frequency. Like if this was producing 100 hertz and this which is received is 80 hertz. When say this was moving at a speed of 20 meter per second. But if we change the speed, if it was 40 meter per second, then the frequency heard will be or received will be much smaller. So it might be 60 hertz. So if the object is accelerating, like if it was moving at a constant speed, then there will be a frequency will be greater, but it will not change. But because this object is accelerating, continuously changing the speed, as a result, the frequency, every time the frequency received will be smaller than the actual frequency and it will continuously, not decreasing, I mean increasing. Because if it is 100 hertz, it will be 120 hertz here. And this will be like example 140 hertz. No, frequency does not decrease. I mean in terms of wavelength will decrease, frequency will increase. So this example, the source frequency is 100 hertz. Because the source is moving towards the observer, so the observed frequency will be higher. That is one thing. And because the source is accelerating, so if the source like travel at a speed of 2 meter per second and the source travel at a speed of 4 meter per second, the 4 meter per second will cause a greater change in the frequency. So if it was 100 become 120 because of 2 meter per second, with the 4 meter per second, it will be a higher change in the frequency. Because the speed at which the object moves, that also affects the frequency. Because we have the formula that observed frequency, if the observer is stationary, it will be V, F naught is increasing. So this will be subtracted V minus Vs into Fs. So what is happening to Vs? The Vs is increasing. Like the speed of the source is increasing. So what will happen to the value of the denominator? The value of the denominator will decrease. Is it clear? This question? Another question. Over 20 years ago, astronaut placed the reflectors on the surface of the moon. These are still used by number of observatories on Earth to monitor the distance uh, to the moon by reflecting a pulse of a laser light from them and detecting the reflected signal. Scientists have determined that the moon is at a distance of 363,104 kilometer as it closes and 405,696 kilometer when it is further. It has also been determined that the moon is getting about 3.8 centimeter further away from the Earth each year. Describe how the reflected pulse can be used to determine the distance to the moon. So how we can use these reflected. So this is representing the moon. and there's a reflect, the mirrors are there. So what will happen? The pulse will be sent to the moon, and then that pulse will bounce back. And the speed, we'll use a formula, speed is distance over time, but the distance will be 2d, like the distance between the Earth and the moon is d. So the distance traveled by the wave will be 2d. And if we need the distance, it will be speed into time divided by 2, but that will be the distance. So in words, how you'll write, like the same thing, the time for a return to, we can determine the time taken by pulse to travel to moon and return back, that is t. The speed of the wave, as we are using a light wave, electromagnetic wave, which is a constant, which is 3 exponent 8, a known value. So using the formula v into t divided by 2, we can determine the distance between the Earth and the moon. So you just have to write in words and just 1 mark for formula. An observatory send out pulse of a laser light duration 2 exponent minus 10 second. When it to determine the distance to the moon, calculate the pulse length. So we want to determine the length of the pulse. How we can determine the length of the pulse? This is when we need the pulse length, like the length of the signal. Like what is this? For what distance we produces this wave, that is called a pulse length. No, there's a difference between a pulse length and the distance here. Pulse length means length of the pulse. Like example, when I send a signal, what is the length of the signal? That is called the pulse length. So an observatory send out a pulses of a laser light duration, like these laser were on switched on for 2 into 10 power minus 10 seconds. Yeah, we just need a velocity into time. The laser was switched on for this much time, okay, to produce a pulse. We want to determine this length of the pulse. What is the length of the pulse produced? So how we know this? We know the speed of the wave, the speed of electromagnetic wave, that is 3 into 10 power 8 meter per second. Like that is the speed at which the wave will travel. And it was switched on for 2 exponent minus 10 second. What is the length of the pulse, or what is the distance covered by this pulse in that much time? It's not like total, it's just a pulse length. So what is a pulse length? It's a length of the signal for a duration, like the length which the signal will cover when it is produced. That's the pulse length. So if I need a pulse length, we have the formula, we know the speed and we know the time. So we can use a formula, speed is distance divided by time. So speed into time will be equals to distance. The speed is 3 into 10 power 8, and the time for which it was switched on, that was 2 into 10 power minus 10. So what is the length of the pulse? This is the length of the pulse, which is 0.06 meters. So 0.06 meters is the length of the pulse. Like the pulse which we use, that is having, like when we switch on this laser, how much distance that laser, the length which is covered by this pulse, that is called a pulse length, or the length of the signal, which is 0.06 meters. Is it clear till this point? Or equals to 6 centimeter. And remember the relation, like example, if I'm using, say, an object is there which is having a thickness of, say 6 centimeter, or say 3 centimeter. And I'm using a pulse which is having a length of 6 centimeter. This is the length of the pulse and this is the distance. So whenever we prefer a pulse length, the pulse length should be smaller than the thickness of an object. Why? So that we can distinguish between the pulse which is sent and the pulse which is received. The signal which is sent and the received should be distinguished. If I am using the same length, say I want to determine the thickness of this object, which is 4 centimeter. Or I know the thickness of this object, say 4 centimeter. And I'm using a pulse length. The length of the pulse is 8 centimeter. So when I say length of the pulse is 8 centimeter, so the pulse will travel 4 centimeter and then further travel 4 centimeter. And then I will send another pulse. Once it covered 10 centimeter length, then I will send another pulse. So whenever we select a pulse length, the length of the pulse, it should be smaller than the thickness of the object. What is the reason for that? Because if you select the same, like if you select the longer than the thickness of an object, then you cannot distinguish between the pulse which is sent and the pulse which bounce back. The two pulses, it will be difficult to identify or distinguish between them. So whenever the length of the pulse is selected, the length of the pulse should be shorter than the thickness of an object. Because it's hard to distinguish what we want to do. We want to send the pulse, it goes inside and then it bounce back and return and we receive that. But if I use a pulse which is having a length of say more than 4 centimeter, then what will happen? The pulse is going and then it is returning back. So the two pulses might mix or interfere with each other or combine with each other. So it will be difficult to distinguish between the two pulses, that which one is sent and which one is received. That's why whenever we want to determine the thickness, we always prefer a pulse with a shorter length. So it will goes, when it bounce back, it return to us. So the pulse length should always be shorter than the width of an object. Like here, you see we send a pulse. In this one, we send a pulse. So when we send the pulse will go inside, bounce back, and then return. But if I'm using a pulse which is a longer pulse, like example, I'm using a pulse, so it is going, it hit and bounce back. So still we are producing a pulse and the one which is bouncing back. So these two signals will interfere, and as a result on a transducer, it will be difficult to distinguish which one is from the reflected one. But if you use a smaller pulse duration, say we produce a pulse here. So example, this is representing a pulse. So we produce a pulse. So this pulse is going, hit, come back. But if you use a longer pulse, then what will happen? When you use a longer pulse, still you're producing a pulse and the pulse is bounce back. So you're producing a pulse and the pulse bounce back. So first thing, these two signals can mix with each other. So, and it will also become hard to distinguish which pulse is reflected and which one you're still producing. So whenever we use a pulse, we always use a shorter pulse so that it can go inside, strike and return back. So always the short pulses are used. Is it clear, the concept of the pulse? So now next question, discuss whether the level of the precision quoted for a distance to the moon and its rate of increase in distance from Earth are justified. Look, as you see in the question, it is mentioned that moon is getting away 3.8 centimeter each second. Each year. So every year, the distance of the moon is increasing by 3.8 centimeter. So moon is here. Now this is a new position of the moon. And this distance after 1 year is 3.8 centimeter. And we are using a pulse. In the last question, we calculated the length of the pulse. The length of the pulse we used was 6 centimeter or 0.06 meters. Is this length of the pulse is okay to measure this 3.8 centimeter distance? Yes or no? So it's not suitable. Why? Because the length of the pulse, it's not acceptable because 6 centimeter pulse is longer than 3.8. So the correct answer, we will say, how you write the answer, you will say no. It's like the discuss whether the levels of the precision quoted in the distance to the moon and its rate of increasing distance from justified. So we'll say no, it's not justified. Why? Because the distance, the length of the pulse is 6 centimeter, or a pulse length is 6 centimeter, which is longer than the distance moved by the moon. So it cannot be determined precisely. Minimum should be, the pulse length should be smaller than 3.8 to determine this distance precisely. Is it clear? So whenever, remember this rule that whenever we use the pulse, the length of the pulse, the length of the signal or the time of the signal is always smaller than the width of the object. Another, a round trip for the light pulses take about 2.8 seconds. As many as 10 pulses per second may be used. State why pulses are used rather than a continuous beam. Like they're saying, why we did not use a continuous beam, like continuously we are sending the signal and we receive it back. What is the reason why a small pulse is sent? So why the pulse is sent and received? So the structure answer, so that we can tell which receive pulse matches with the send one. Like one can be sent and received at the same, and no interference or no, the two pulse will not mix with each other. When why we are not sending the continuous wave? If we send a continuous wave, we cannot distinguish between the pulse which is sent and the pulse which is received. Because how you will distinguish the pulse which you are sending and the pulse you receive? If you are continuously sending like you send a continuous beam, so it's hard to distinguish which is sent and which is received. So that's why we use a small signal, small pulse, so that one can be sent and received, and then we send another one. Is it clear? Another observatory uses a high power laser. The laser produces a pulse duration, which is 1 exponent minus 10. The energy of the pulse is 115 millijoules. Calculate the power. So power is energy divided by time. You have the energy, which is 115 milli. So 115 into 10 to the power minus 3. And the time interval is there, which is 100, sorry, 1 into 10 to the power minus 10. So when you divide, you will get the power. What is the power of the laser used for this? It will be joules per second or a watt. 1.15 into 10 to the power 9. Okay. So 1.15 exponent 9 watts. Yeah, 1.2 exponent. The next question, the wavelength. The wavelength of a light produced by the laser is 5.32 exponent 7 meter. That's the wavelength of the wave which is produced, the light wave. And the light is emitted from the aperture of a diameter 75 centimeter. It suggests using a concept of diffraction why such a large aperture is necessary. Remember, recall the idea of a diffraction. Diffraction means spreading of the wave when it passes through the obstacle, passes through the gap or so diffraction means when the wave passes through the gap or the edges, that is called diffraction. And diffraction depends on the wavelength and it depends on the gap size. If wavelength is approximately equals to gap size, then we will have a maximum diffraction. If the wavelength is greater than or wavelength is less than the gap size, then we'll have a minimum diffraction. Aperture means like opening, gap between the two objects, that is the aperture. So they mention that the light which the aperture is 75 centimeter or it is 0.75 meters. Okay. And the wavelength which is used, the wavelength of a light which is used is 5.32 into 10 to the power minus 7 meters. So why such large aperture is necessary? So what is the reason why we are using a large aperture or a large gap? So because as we know the diffraction, as a result of a diffraction, as the light is coming out from this aperture, if the diffraction happen, the light will spread out. If the wavelength is equals to the aperture size or the gap size. But because the wavelength is wavelength in this case is shorter than the gap size, so we'll have a minimum diffraction. And when the diffraction increase, the intensity of the signals will decrease. So as a result, when the aperture is greater than the wavelength, minimum diffraction, so we'll get a maximum intensity of the signals. Is it clear? No, we don't want a diffraction to happen here. We want a minimum diffraction because we are sending a laser. A laser is like a light. A laser light is sent. So we want it to go straight, not spread out. That's why this aperture or a gap is more than the wavelength. So it will not diffract. Otherwise, if it was equal, then a maximum diffraction will happen and it will spread out. So as a result, what will happen if the aperture was equal to the wavelength, the diffraction will be maximum and the intensity of the signal will be lower. So it will be, we want a high intensity signal to send so that it can be received on the moon surface and bounce back. Which of the following would allow the level of a detail in an ultrasound scan to be increased? How we can make a, like when we say a level of a detail means we want a signals to be smaller, the wavelength to be smaller. Which one, like whenever we want a more detailed scan, when we say more detailed scan means we want a shorter wavelength. So which one will reduce the wavelength? Increasing a duration of the pulse. If you increase the duration of the pulse, it will not make it proper because if a pulse duration is longer, like of a longer time the pulse is sent, then it will be hard to distinguish which one is sent and which one is received. Increasing a frequency, so we have the formula V is equals to F lambda. If we increase the frequency, the wavelength will be shorter, and shorter wavelength give a more detailed image. Increasing the intensity of the ultrasound, it will reflect, it will give more, not detailed image, but it will give a highly concentrated of the focus image. But not a, when we say a detailed image, what does it mean? It means we want more point of reflections. And more point of reflection within an object depends on the wavelength. Shorter wavelengths are there, so more point of reflections. In this question, engineers are developing a system using a Doppler effect, which will detect the movement of a people in a room during a hostage situation. The system make the use of the Wi-Fi transmitter already in the building rather than needing a separate transmitter. The system is shown in the diagram. So a detector is placed outside. So here's a detector outside, which is receiving the signal from the Wi-Fi transmitter. And the signals which are from a person reflected from a Wi-Fi signal which are reflected from a person and received by the detector as well. So a Wi-Fi transmitter along a path, it also receive a signal reflected from a person in the room, which will have travel a path X. The Wi-Fi signals have traveled from X to Y and then Y to Z, and another one received directly. Explain how the system uses a Doppler effect to detect the motion of the person. So how a motion of the person can be detected? So what will happen? First, we receive the radiation or the frequency or the wavelength from directly from the Wi-Fi transmitter. And then the signal which we receive from the reflected from the person, we will detect the radiation or the frequency and the wavelength of that signal. And then we'll compare. If we find that, for example, the Wi-Fi signal, the frequency of the signal which we received directly from the Wi-Fi transmitter was 100 hertz, but the frequency of the signal which we received from the person, reflected from the person, is 120 hertz. So what that means? It means the person is moving towards us. And if the frequency of the signal which we receive reflected from the person is like 80 hertz, so it means the person is moving away from us. So how to write the structure answer for this? First thing, you'll mention like we'll record the signal from the Wi-Fi transmitter and we'll record the signal from the reflected from the person and compare the frequencies. If the frequency reflected from a person is higher, it means he's moving towards, and the frequency received by the reflected like from the person is lower, it means he's moving away. So we can detect the motion of this, or if there is no change in frequency, it means the person is stationary, not moving. Is it clear, this one? Suggest an advantage of pulse echo technique over this system. Like this system is there and the pulse echo technique over this. So what will happen? Using a pulse echo technique, we can first thing, so advantage of the pulse echo technique over this system, like this system is there and we have a pulse echo. In a pulse echo technique, it can be